So hello everyone, I'm Rolland from second year PhD student in Paris. I'm working with Pascal Roberto, Yanis Kuipers and Francesco Dovidio. And I'm working on the role of the mesoscale-wave interaction on the energy transfers in the Sicily Channel area. So this work is part of the story of how mesoscale kinetic energy is transferred to smaller scales and finally to how it dissipates. Because mesoscale wave interactions were identified as one of the possible routes to transfer this mesoscale kinetic energy to smaller scales. I will just show you two examples of those interactions. Here you have idealized mesoscale resolving simulation conducted by Barkan et al. In 2017. That is representative of the Antarctic circumpolar current. So they have two simulations, one with low frequency wind forcing that create doesn't create near inertial waves, and another one that creates lots of near inertial waves coming from high frequency wind forcings. So as you can see, you have lots of difference in the dissipation rate of the turbulent kinetic energy. You have 2 to 3 orders of magnitude higher of the dissipation rate in the high frequency wind forcing simulations, especially around mesoscale structures. And Barkan et al. Identified 2 mechanisms that explain those differences: direct extraction of the mesoscale kinetic energy by the near inertial waves, and what they call stimulated imbalance. So it's the presence of near inertial waves trigger a forward energy cascade from the mesoscale to the submesoscale, and another one from the submesoscale to near inertial waves. Here you have another example. So it's a study of Ajayi et al., which is actually in review. They studied the impact of internal tides on the energy cascade using the NEMO Inatel 60 submesoscale permitting model. So they are looking at this model in the North Atlantic, and they computed the spectral kinetic energy fluxes. So what you can see, I think you don't see my pointer. What you can see on the right figures is that for a positive value for a given length scale, you have a forward energy cascade if you have a positive value, or inverse cascade if you have a negative value. So what you can see, so they have 2 simulations, one with explicit tidal forcing, the with tide simulation, and another one with no explicit tidal forcings, the no tide simulation. And what you can see on the fluxes is that in winter, you have a weaker inverse cascade in the presence of internal tides. And in summer, you have an enhanced forward kinetic energy cascade at large scales and also at small scales. So you can see that you have an impact of the presence of the internal tides. So there are still open questions. For example, what happened in realistic situation, in contrary of Barkan et al.? What happened in coastal region, or when you have lots of asymmetric constraints? And also what happened when you have near inertial waves and internal tides at the same times? And also what are the mechanisms? So to try to answer those questions, we wanted to characterize the waves and the mesoscale dynamics in the Sicily Channel area, and to quantify and localize the energy and energy transfers across scales in this area. So why the Sicily Channel? It's a region with lots of high mesoscale activity. As you can see on the top right figure, you have a well-identified eddies and mesoscale currents. You also have a sharp topography, and it's a coastal area, and also it's one of the hotspots for tidal motion and dissipation of turbulent kinetic energy in the Mediterranean. So we have everything we need to answer those questions. So here you have the model characteristics. So we are using also the NEMO Inatel 60 simulation. So we have Harley outputs, mesoscale permitting simulation. The wind forcing are coming from ERA interim with 1/3 degree and 3 Harley outputs. For this work, we have 2 months in summer, August and September, and we will add a July in the next weeks, I hope. And we have 3 months in winter, July, February, and March. And finally, we have the with tide and the no tide simulation as for Ajayi et al. So we are now moving to the results. So here you have the vorticity, the snapshot of the vorticity, the middle of August. On your left, you have the with tide simulation. On your right, the no tide simulation. So what you can see is that we have similar structure between the two simulations with large eddies and smaller ones. We have lots of fronts. But the one thing you can notice is that the vorticity has a rougher aspect in the with tide simulation. So that is just the imprint of the internal tides on the structures. And if we look at the vorticity in the middle of February in winter, we don't see clear. We don't have really much differences. We have also similar structures, and we have in the two simulations lots of very small scale structures. We are now looking at the power spectral density of kinetic energy in the domain at the surface. So in red, you have the summer, in blue, you have winter. Dotted points are for the no tide simulation, and the solid line is for the with tide simulation. So what you can see is that we have in both simulation, in both summer and winter, near inertial waves and tides. So we have two constituents of the tides, the semi-diurnal M2 and the diurnal constituent K1. You can see that we have stronger tidal harmonics in summer. And also, if we zoom on the inertial peaks, you can see that we have different different aspects, different shape of the inertial peak in the inertial band of the domain. So we have here an information about the distribution of the inertial energy in the domain. It's not clearly visible here, but we also have energy in the diurnal frequency band in the no tide simulation, because if we look at the wind at 10 meters, at the power spectral density kinetic energy, you can see that we have an intense thermal breeze that will create a motion, a diurnal motion in the ocean, even in the no tide simulation. If we now look at the spatial distribution of those three frequencies, so here we are looking at the kinetic energy of the inertial frequency bands. What we can see is that on the southeast of the domain, we have lots of energy in summer, and in winter, the energy is distributed more on the north of the domain, the northeast, and a bit on the southeast also. So the results are similar for the no tide simulation, so I only present here the with tide simulation. So this distribution is in a good agreement with the wind power input to inertial motion that we computed, and I show here. And what you can notice is that we have a low kinetic energy level in the Sicily Channel. So this is in agreement with the mooring data we have inside the channel. You can see we don't have a peak at the inertial frequency here. So we try to understand why we don't have this peak here, and so we looked at videos of the zonal velocity filtered at the inertial frequency, and what you can see is that the length scale, the spatial scales of the inertial motions are too large to go through the channel that is very narrow. And if we look on the vertical, so here we look a north-south transect from the Tyrrhenian to the Gulf of Gabes. You can see that also the channel is too shallow to permit the motion to go through it. A last thing about the inertial frequency band, we were able to look at to find what we call the chimney effect. So it's the trapping of near inertial kinetic energy inside anticyclones. So you have an example here on the southeast of the domain in summer. And if you want to learn more about that effect, you can read Rolland et al. 2020. So here you have an example of Eddy near inertial wave interaction inside the model. Now, if you look at the semi-diurnal frequency band, so the one of M2 tidal constituent, you can see that it's more simple. We have 3 generation sites: the Sicily Channel, the Gulf of Gabes, and the Messina Strait that is well known for its solitons. You can see that M2, the internal tides of M2, can propagate in the domains. It's especially true in summer. And these results are in good agreement with the tidal generating force computed from TPXO9 following the methodology of Baines. And just to have a quick view, you can see here the zonal velocity filtered at the semi-diurnal frequency, so you can see the propagation of the tides. Now, if you look at the diurnal frequency bands, it's a bit more complex because we have a mix between the diurnal, lunisolar diurnal constituents of the tide K1 and the motions that are generated by the thermal breeze. So first for K1, you can see that we have 3 generation sites: the Sicily Channel, the shallow shelf southeast of Sicily, and some highlands near the Sicily and the Tunisian coast, but also a bit on the Messina Strait. K1 is subinertial, so the internal wave generated are trapped by the topography. That's why we don't see propagation inside the domain as for M2. But what we can see is that on the summer at the surface, we have a background that is relatively high compared to the other figures. So this comes from the thermal breeze, the motion that created by the thermal breeze in summer. And you can see that we have 3 hotspots of diurnal motion outside the generation of tidal internal tides. So they coincide with the presence of high level of diurnal wind kinetic energy, so the famous thermal breeze. And if we look at the zonal velocity filtered at diurnal frequency, we can clearly see those motions traps inside anticyclonic structures, so anticyclonic eddies. And this is due to the trapping of those motions by anticyclones because of the effective inertial frequency. So the effective inertial frequency is the sum of the local inertial frequency and the half of the relative vorticity. So in anticyclonic structures, you can generate internal waves at subinertial frequency, for example, at the diurnal frequency. So here you have the effective inertial period centered on 24 hours, and you can see that it matches the 24 hours matches well with the high level of diurnal kinetic energy. So you have another example here of internal waves eddy interaction in the model. So finally, from all those results, we identified 4 different areas that are dynamically contrasted in terms of wave dynamics. So you have the 4 regions with the frequency you can find in it. And we were interested by computing the spectral kinetic energy fluxes as in Eddy et al. In those 4 regions, and try to find differences and maybe try to explain those differences, and try to investigate the impact of tides and of the inertial wave on the differences we can see. So here I present you some examples of those kinetic energy fluxes. So it's horizontal kinetic energy fluxes, to be precise. So I will not go deep into the details because we are still investigating, trying to understand those results. But what we identified for now is that for every region, the fluxes are 1 to 2 orders of magnitude larger than in the open ocean. For example, in Eddy et al. We are really strong seasonal and spatial variation of the fluxes in the area. And sometimes we are surprising with tide, no tide differences. So we are actively working on that, and we are trying to understand those differences. So I finished with some key results. So this work was the first global overview of internal wave dynamics in the Sicily Channel area. We understand now why we have no inertial kinetic energy in the Sicily Channel. We identified the generation site of the internal tide in the Sicily Channel, and we also demonstrated the presence of diurnal inertial motion trapping by anticyclones. And we are now working, yes, on the spectral fluxes, and we are trying to understand how to relate them to those interaction or to those wave we found in the domain. So thank you for attention, and if you have questions,